In dehydrohallucination, if we take alcoholic KOH, sodamide, ethoxide ethanol, methoxide methanol, we get ZZF alkene. Whereas if we take a bigger base, a bulky base such as tertiary butoxide in tertiary butanol, we get the Hoffman alkene. You need to remember what is ZZF alkene. ZZF alkene is alkene which has more number of alpha hydrogen, or we can say it is the alkene which is more substituted. So if you see, we have two alkenes CH3 CH double bond CH3, and there is another alkene CH3 CH2 CH double bond CH2. So I think you will agree with me that this has greater number of alpha hydrogens. This is alpha carbon, and this one, the carbon adjacent to the double bonded carbon, is known as alpha carbon, and hydrogens attached to that carbon are known as alpha hydrogen. So this has 6 alpha hydrogen, and this one has 2 alpha hydrogen atoms. This is alpha carbon. All right. So the alkene which has more number of alpha hydrogen is known as ZZF alkene. This is known as ZZF alkene. Whereas the alkene which has less number of hydrogen atoms is known as Hoffman alkene. So Hoffman alkene is the major product when tertiary butoxide, tertiary butanol is taken, and ZZF alkene is the major product when we have alcoholic KOH, sodamide, ethoxide, the reagents which are smaller in size. ZZF alkene is the alkene which is more substituted, and Hoffman alkene is the alkene which is less substituted. Substitution means the carbon change. See, here double bonded carbons are attached, one group and two groups. Alright, and this side double bonded carbon is attached to only one group. So this double bonded carbons are disubstituted, and this alkene is monosubstituted. More is the substitution, it is more stable. Less substitution, less stable. So more stable alkene is formed when smaller bases, and less substituted alkene is formed with the bigger base, because steric hindrance is more. Steric hindrance is the cause of formation of Hoffman alkene with tertiary butoxide, whereas in all other cases ZZF alkene, the alkene with more number of alpha H is formed. Now if we have, let's say, RF, RCl, RBr and Ri, which one will be more reactive? I think you will agree with me that bigger the bond, in Ri the bond is huge. So leaving group ability in I minus is more, whereas in RF the bond is small. The bond is small, so removal of fluorine is difficult. So the reactivity order is RF is less reactive than RCl, then RBr, then Ri is most reactive. Alright. And among degree of alkyl halides, 3 degree is more reactive than 2 degree than 1 degree. This is true for E1 as well as E2 elimination. Alright. Next is a reaction which has a name of acidic dehydration. Acidic dehydration of alcohols. Acidic dehydration of alcohols. Alright. It is an example of E1 elimination. It is an example of E1 elimination. It is again a beta elimination reaction because hydrogen is removed from beta carbon. See, dehydrohalogenation is a beta elimination reaction. Acidic dehydration of alcohol is also a beta elimination reaction because H is getting removed from beta carbon. Alright. So what is the first step in acidic dehydration reactions? First, the reagents. I will give you the reagents. Reagents for this reaction are, see, one reactant will be alcohol, that is obvious, and the reagents taken are, either you can take H3PO4 or you can take H2SO4 or you can take Al2O3. You can take any of these reagents. Alright. So how the mechanism is? See, step 1 in this reaction is protonation of alcohols. See, if you take H2SO4, I think you will agree, this gives H plus and HSO4 minus. First ionization is always good. So if you have alcohol CH3CH2OH and the medium has this H plus attaches to lone pair of oxygen atom and a protonated alcohol is formed CH3CH2OH. It gets a plus. So, formation of a protonated alcohol is the step 1 and we will be studying more about this further. That is it.